Good morning. I think we're about to start. I noticed that most of the people are in their seats. This webinar is intended primarily for people using our fantastic integrity software, which you can download from our website. We've already completed the level 1 webinar, so this one we're moving into level 2, which is primarily meant for testers. We're going to start out with Nfpa. It's a little simpler. Let's just take a look at a few slides here. So, big change from 2001 Nfpa to 2012, where they required a minimum concentration of 85% of design held at the highest level for 10 minutes. The first time that 10 minutes has ever appeared in the standard actually appeared in the 2008 version, which was a bit of a total mess, and it took a total rewrite to get it to say what it was supposed to say. It must have had 50 mistakes in it at least, so if you're trying to use 2008, at least the enclosure integrity portion, I would advise against it. I really should get a 2012 version. These are some of the key differences that occurred going from 2000 to 2012. Was something that I labored on for about 5 years or so, and there were reasons for it. It enabled us to get longer retention times and more favorable peak pressure evaluations, removing some of the unnecessary conservatism that was in there, and I'll explain to you later how that happened. But we can see here the old Nfpa on exactly the same test data would get a 9.3 minute retention time, 382 Pascal peak pressure, and on the new Nfpa we would pass the hold time about a 10-12% improvement in hold time and about a 40% reduction in the peak pressure. Even more of a change with the halocarbons, where we go from 7.3 minutes to 10.3 minutes, and the peak pressure drops from 373 to 247. So huge advantage to you in going to the 2012 version. That's what we've modeled our new enclosure integrity software on, and it would mean, say, for the inert agent enclosure, that we might be saving $20,000 in air sealing or something. Air sealing can be expensive. I've known of many people that have spent a small fortune trying to get these rooms tight enough, and so the advantage of using 2012 version is that we've made life a bit easier for you. So this is a depiction of one of the reasons why life has gotten easier, and that is that the Nfpa calculations work effectively on hole size, and holes are not all created equal. Different types of holes respond differently to different pressures. So if we were to cut a hole in a flat plate and measure it at 10 pascals or 125 pascals or 250 pascals, it would always come out at the same size. We could measure that size. If it was 100 square inches, it would be 100 square inches at any one of those pressures, based on this flow formula that says area is equal to the flow divided by the square root of the pressure. Well, for certain types of leaks where they are long contorted leaks going through small cracks and so on, we have a fair amount of laminar flow in there. What that does is it changes part of the relationship to flow is, or area is equal to flow divided by pressure, and the combination of the two gives us some kind of a combination exponent that's between 0.5, which is square root, and 1, which is laminar flow. And in this case, the example that we're going to be using today, we have an exponent of 0.71. So that's a little bit more than the square root, but not quite as much as a power of 1. So what that means is that when we measure a hole size in the example that we're using at 10 pascals, we say, aha, the hole's 257 square inches. Isn't that nice? or the equivalent hole is 257 square inches. But at, in this case, a higher pressure of 125 pascals, which is where we measure for pressure relief venting, we say, aha, that's 443 square inches of leakage. Now, if we were to go in the opposite direction, we would find that for low pressures, around 1 pascal or so, which is where the inert agents leak out, that the enclosure is actually tighter, or apparently tighter. So we get a more accurate prediction of the hold time and a more accurate prediction of the peak pressure, and both of them are less conservative than they were before. The question here is hold time prediction fantastic based on 85% of design concentration. The current version of Nfpa, and probably for some time, 4 or 5 years or so, counts all concentrations as being the same for descending interface, but not for continuous mixing. So its model is of a sharp interface, which means we've got air above, agent below, and we go from 0% air to, let's say, 10% agent, and there's no interface in between where it goes through a transition. And I'll show you some pictures of that later. So they're actually all the same. Interestingly enough, what happened when we did the hold time research is that we found out that the halocarbons in particular actually just seem to predict about 85% of the initial concentration. I won't go into this. I'm going to back. This is going to be a bit complicated at this point, so I'm going to back into this a little bit later. Now I'm going to jump over some of these slides here. For those of you doing ISO, the 2006 version has gone just the other way and is using a wide interface, which has now decreased the hold time by 25%. In addition to that, a lot of people take note of the fact that the standard requires a descending interface to hold to 90% of enclosure height, which causes the enclosures, or forces the enclosures, to be incredibly airtight and forces them to have vents all the time. So very different situation with ISO primarily used in Europe and Nfpa primarily used in the US and probably Southeast Asia. So let's take a look at peak pressure. There's your inert short spike followed by a very rapid drop-off. There's your halocarbon. What's interesting about some of the standards is they actually only predict positive peak pressures for halocarbons, and we can see that they definitely have negative and positive spikes, and this is very characteristic. The size of this negative spike is determined to a large degree by the humidity. The drier the air is, the bigger that spike is. The more cooling we get, so humidity becomes an important factor with halocarbons. I usually dwell on this a lot longer, but I'm not going to today. I just want to touch on it. So in the case of whether it's inert or halocarbon, the degree or the size of the negative and positive spike is directly determined by the leakage in the enclosure or the enclosure plus vents, depending on what we're counting. And we wind up with a leak to volume ratio. Now, in some cases, people are using peak flow rates. Peak flow rates imply a leak to volume ratio. And leak to volume ratios imply a peak flow rate, because if you've got a certain volume, it's going to require a certain flow rate to get the agent up to concentration. So they don't obviously appear to be the same, but they are actually the same. So leak to volume ratio is a very convenient way of defining an enclosure. So if we have an enclosure of a different size, if it has the same leak to volume ratio, then it will develop the same peak pressure. So all we need to know is how much peak pressure do we get with certain leak to volume ratios, and bingo, we know what the peak pressure is going to be, as long as we know the characteristic of the valve, or whether it's a quick opening valve, which it is in most cases, goes boom, it's open, or it's a regulating valve which is starting to be used more with inerts, in which case it regulates the flow, and the flow is more continuous over the whole period of the discharge. So here we have the humidity. In this case, this is negative pressure. As the humidity goes down, you'll notice that the correction factor goes up, so we get more and more peak pressure, and we get a slight reverse on the positive peak pressure. As the humidity goes up, we get a little bit more positive peak pressure, not a lot more. It's mostly because of the fact that we're not going negative, so it tends to allow the enclosure to go positive more. So we won't get into the design too much. There are changes in the Nfpa working plans in section 5.1.2.2 you should be aware of, or Annex D12, that the standard does require the enclosure to withstand the peak pressure. This is really the big change that is being imposed upon the Nfpa testers in the US, who basically have not really had to look at peak pressure. They now have to do an estimate of the maximum peak pressure, and they have to specify the enclosure pressure limit. So these are two new things that have to be done, and this is all reflected in Enclosure Integrity software and the training, which we'll get into in a moment. One of the things that we found out in our study was that most of the peak pressure formulas being used are wrong. They're not wrong at all pressures, but are all leak to volume ratios. And here we have leak to volume ratios on the side. But the power that they use in the curve is actually the wrong power. So as a result, the shape of the curve is incorrect. And what that means at a lot of leak to volume ratios, and this is very typical for a 10-minute hold time, would be a leak to volume ratio of around about 16 for a halocarbon. For an inert, that we find that we have an under prediction of peak pressure by 200 or even 400%, depending on the formula. So people say, oh my God, the formula that I've been using tells me I have only 100 pascals and you're telling me 400. Our formulas are based on extensive testing, and which has never been done, was done over a period of 5 years. All of the agent manufacturers were involved, and I think it's certainly the numbers to use. And they go under FSSA or FIA. They're kind of written into, they're not really standards, but they're kind of bodies that kind of say, yeah, you can use this. So Fantastic Integrity, which we'll open up in a minute, will calculate the PRV size required. We have a designer's version that's coming soon. I'll give you a preview of that if I remember to show you. Why don't I just show you now, because I'll probably forget. Let's just close that one down and open up. The version I'm opening right now is our development version, and we're still vetting it to make sure it's okay. And I'm just going to drag that over to the screen here so you can see it. There it is. And when we go into Tools, we have Venting Calculator, and this little venting screen comes up. We had this in the form of an Excel spreadsheet, and there's a number of problems with it and so on. So we decided to put it into our software. We're still working on it, still improving it and so on. It's relatively simple. It allows you to do an enclosure analysis, change all the important variables before the enclosure is designed, to see what kind of problems you're going to run into when you get down to testing it. And you can change agents, you can change heights, you can change concentrations, and see what that results in terms of peak pressure. So let's say that, let's just do one in Imperial here. We're going to use FSSA venting equations 2012, descending interface, argon argon, argonite, pretty close to being the same thing. 60-second discharge time. This is the volume, maximum flooded height, the enclosure pressure limit. This is set in pounds per square foot, interestingly enough. Minimum protected height, let's set that at 7.5 feet just for fun. Do a little calculation, and here it's calculated the vent that's needed. If we decide we're going to use enclosure leaks, in this case we can have a maximum of 1,000 square inches of enclosure leaks. For hold time evaluation, if we use this for venting, let's say, we'll just use 100% of that. Oops. 100% of that for venting. We still need a pretty large vent here. So this is a situation where we can tell by this analysis that we will need a vent. Just running over this real quick to so this is an enclosure that will need a vent. If we were to change, let's say, concentration, we'll notice that the vent size changes. If we were to change the minimum protected height, it doesn't change the amount of venting that's needed, but it does change the amount of enclosure leakage that you're allowed to have, which you could use as venting. So that's our little venting calculator. That's not really the purpose of the webinar today, since that's more on the level 1, the design part. So level 2 is really about doing the test. So this venting calculator is designed to be used before the enclosure is built, and the rest of the enclosure integrity is designed to be used after the enclosure is built and you come by to determine what the hold time and what the peak pressure will be. So this is a test that I performed earlier. We'll just click on this real quick. I'm going to run through the different screens that you see here. Oh, incidentally, I did talk about, this is the sharp interface where we've got agent in red, air in white, and you can see it's a clearly defined interface, much like water in a cup with air above, water below. The wide descending interface says that the gradation between air and agent continues to widen and widen. It doesn't actually work like this at all. It goes to a characteristic thickness and stays there. So the truth of the matter is somewhere in between the two. So let's just rocket back here. There we go. So let's take a look at enclosure integrity. So each of the sections in enclosure integrity, I'll just wrap them all up here so you can see. Each of the sections, testing, technician information, equipment, building agent details, enclosure, leakage, venting, and peak pressure analysis, each one is conveniently on its own. It's not really a tab. It's kind of like a vertical tab. So we can expand those sections and leave whichever sections open that we want. And then once we're done with them, we can contract them and keep the sections that we want to look at expanded. So it's a very convenient way to kind of jump around. Our analysis goes in a linear fashion, so if we keep testing, we just keep dropping down, down, down and doing more and more tests so we can see the whole thing at once if we want to scroll with a scroll bar, which is here, or we can collapse them onto our screen. We can also, of course, resize to whatever size we want, which is pretty useful. So let's just contract it down and take a look at one section at a time. So the very first one is test technician information, and I'll just put in the level of my training. We won't bother with that. So let's say we're done with that. The next one is the equipment, and if you use the same equipment over and over, you can merely do a save as on these files and title them whatever you want. So when we go to open them, you'll notice that we have all these files prefixed with the name of the test, in this case Nfpa, ISO, and I think that means US units. ISO is always in metric units, and it's suffixed by the date in year, month, day, hour, minute. So these will always sort by date. So that date is put on there automatically. So whenever you're doing a test, you know exactly the chronological sequence of the test as you ran them. You may want to go in and change those dates. You have the option to do that. Or in the case here, I've actually done a save as, and I've added something onto the end of it, where in this test I've got vent only. So it enables me to very easily look at my files, move them around, and so on. And I think these are in XML format. So this, I think this is the one that we're on right here. So we can see this is the file name up here, and that's the version number that we're running. So I'll just bleep out of that for the time being. So gauge, serial number, this would contain all the calibration information and so on. And these are all the different gauges that we can use. When we click on the fans, we get a nice little picture of them, so we don't have to make a mistake and choose the wrong one. So try and make that visual for you. So nothing special there. We take a look at building details. If we're going to be testing this building over and over, then obviously we only need to fill this out once. If we want to repeat the test, we can do a save as. We can keep everything that's in here and repeat as many tests as we want in the same building. Come back a month later, do a save as, keep the building details, then take those files and put them into, you know, whatever file folders you might want. I think it's in Tools. It tells us where the files are kept, I believe. I'm not good at this kind of thing. Oh, here we go. It tells us where the files are actually kept, and you can change all that stuff. Incidentally, also in Tools under Advanced Options, we're cleaning up these menus to make them a bit easier to operate. We can set the default standard to whichever one that we want, and they're all listed in there. We can also set the language. There's another place to change the language as well. This is being cleaned up and made a little bit easier, which you'll see probably in about 2 weeks or so. Some of the redundant things that you don't have to do are being taken out. Like some of these things like covering fans before taking the baseline and so on. We're simplifying all that, making it a little bit easier for you. Here, venting and peak pressure equations for Nfpa testing. We FSSA, so you can use whichever equations you want. So here we can default to the equation we use all the time. So we set it and we forget it from then on. Venting and peak pressure equations for ISO testing. In this case, we show VDS, then we just change that to FSSA so we have the same in both. So we say OK. So here, elevation has a slight correction. Let's see if we have any notes on this. No, we don't. On some of these, if we hover over, like in this one, if we hover over protected enclosure volume, it says maximum intentionally flooded enclosure volume. Here, if we hover over enclosure protected height, it says measure from the lowest in unhovered to the highest point in the protected volume. And a little bit more information as to exactly what's being looked for in here. Not all of them have extra information, but that's a way to give you some guidelines as to what's going on here. Protected enclosure volume. Now, this is we are changing the wording here to I think the flooded volume, the total flooded volume. So if we have a suspended ceiling, that's not the volume above the suspended ceiling if we're not flooding there. It's only the area that we're flooding. Again, the enclosure protected height, this would be the maximum flooded height. So if you're only flooding to the bottom of the suspended ceiling, it would be the height to the bottom of the suspended ceiling. If you're flooding above the suspended ceiling, it will be to the deck above. And it will also be, if you have a false floor, to the bottom of the false floor. So to the concrete slab below. If you've got some kind of a trench down there and there's not much leakage in the trench, we won't use that as the point from which we measure the height unless that's where the leaks are located. So something that's a relatively small feature like that we'll tend to ignore. And the minimum protected height, which is used in the descending interface calculation. So that takes care of this section. Operating temperature, I think this defaults to 32, so you have to watch that one. Usually 70 is used. Bias pressure during hold time, you notice that we use the variable designations that appear in the standard, in this case PBH, for the pressure, bias H for hold time. That's something that we have to think about. If you know that the enclosure is designed with the HVAC running, perhaps pressurizing the subfloor, and the subfloor pressure is at 25, then that pressure would be 25 pascals. If we know that all the air handlers are shut down, even though there may be pressure there while you're testing, then this is the pressure that you expect to be there during the hold time when the system actually discharges. So in most cases that will be 0, but it can be a significant value. In one nuclear power plant I did once, I believe they held that pressure at 125 pascals. So clearly that was a major determinant in the agent loss. I'll just toss that in later and see what the results would be. So here we have descending interface. You do have to make a decision as to whether it will be descending interface or continuous mixing. Continuous mixing if the air handlers are continuing to operate. Continuous mixing is necessary if you're trying to protect the cables, the top of the ceiling. And I would say for those ISO testers out there that you're always advantaged by using continuous mixing, simply because you will always get a longer retention time, because you have to hold concentration to 90% of enclosure height anyway for descending interface, and it requires the enclosure be ridiculously tight. So I would say that the best design decision you can make for any ISO enclosure is to encourage continuous mixing throughout the whole time period. However, we have this one set at descending interface. We've got FM200 in here, HFC 227EA, and it comes in a variety of different names, and I think we have some of them in here. There's another one. This is FE227, which is DuPont's version of it, and I think there's some other ones in there as well. They all act exactly the same way. We just put the name that the manufacturer uses in there. Here we can decide on the agent quantity by concentration or by weight. Now typically when you're actually performing a test, you're pretty much always looking at the weight of agent that is there, and you're putting the weight of agent in there. If you're just kind of fooling around and you have no idea what it would be, then you would put in the percent and it will calculate how much mass it will take to get that percentage. But in this case, let's just say that we have 500. We want to do this by mass. So let's say we've got 500 pounds. So that's going to give us 6.9% initial concentration. Oh, that's not enough, so put a little bit more in there. There we go, 550 pounds. And that's giving us a 7.5% concentration, and for a specified hold time of 10 minutes. It's not always 10 minutes. Just talking to the fellows at 3M yesterday, and they're asking me if they can put in 20 minutes for Novak in a turbine generator? Absolutely. Put any time you like. Sometimes it's 20, sometimes it's 30. It's commonly 10. Turbine generators are usually set at 20 minutes because there's so much heat involved there that the chances of reignition are extremely high. So they would normally set those at 20 minutes. For a very small enclosure, say less than 200 square feet footprint, you should consider having a shorter retention time than that if the response time of, I think they're called authorized personnel, is less than 10 minutes. So in some cases, there might be a control room right next door. It's going to take 2 minutes for someone to walk across the hall and check it out. You could, in a case like that, set the specified hold time for 2 minutes. And it's okay to do that with small enclosures. They're very, very expensive to get tight enough, and there's no real point of doing it if there's not a lot of mass in there and so on, where you can get deep-seated, difficult to extinguish fire. So those small enclosures, you can set the specified hold time down as low. I think you can set it down as low as 2 minutes for a tiny enclosure, let's say 100 square feet or less, if there's somebody right next door. And if the facility is manned 24 hours a day, I don't see a problem with that. The moment you open the door, the hold time or enclosure integrity is shot anyway. So what to do about that? So those are the building agent details. So let's take a look at the total enclosure leakage. So here we have, it actually shows pressurization, pressurization. The reason for that is that I haven't put a minus sign on here, and when I do, you notice it changes to depressurization. So in this case, we need to tell the gauge exactly what it's showing. The gauge will display minus 10 or plus 10. Once we put one negative in here, it turns this to a negative as well, you notice, and then says, aha, you're doing a depressurization test. In this particular case, we have our test fan one. We're only using one test fan. Typically, we will only use one. We do have the option here of actually adding a fan and running 2 fans. So we just hit the positive here, and we can add a second fan. We don't need to do that here. Here, when we click on the range, we see the ranges pop up, and we can actually get a visual on the range. This is perfect for the authority. Probably the single most important thing the authority could watch, if they watch anything, is to make sure that the range that is used here is the one that was used on the fan during the test. Each time you change ranges up, you have the retention time, and each time you change them down, you double the retention time. So this is probably, if the authority did nothing else, it would be to make sure that the range that was on the fan during the test was the one that was used in the software. That's why we provide these wonderful little pictures, so you can see exactly what the ranges look like. You can also enter CFM directly from a different fan or some other flow measuring device that you might have put your hands on. So you can enter it in CFM, cubic meters per hour, liters per second, whatever you want. No flow is used if you've got 2 fans and you might be using, say, 1 fan for the 10 Pascal test and 2 fans for the 50 Pascal test. So if you've got 1 fan shut off, you say no flow, so that fan is ignored. So for those of you that are familiar with the enclosure integrity test, you've been doing tests for the last 20 years, testing roughly at 10 Pascals positive, 10 Pascals negative. The big change here is we're testing at 10 and 50. The advantage being, what I was showing you earlier was that enables us to differentiate between, say, the assumption that Nfpa used in the old versions that n equals 0.5, which is the square root, and we get the real value in there, and we see that our peak pressure is, the vent area that we have here is going to be much, much greater than it would be using the 0.5 assumption. So we get a huge advantage by taking the 2-point test, and it's the 2-point test that gives us this n value. And if we take a look at this, we'll see here that we have an n value of 0.71. This one has an n value of 0.71 also. and I think we average that to 0.72 or something. So this is where it shows up. These detailed results are hidden most of the time. You don't really need to take a look at them, but you can if you want to. So this leakage area at 10 pascals is 257 square inches. So we'll just get rid of those detailed results. So this is the door fan data that we entered. The building pressure, the fan pressure, and of course typically these will be 50.1, 50.2, 52, 53, that kind of thing. Usually you'll put that on time averaging and enter those. The software is not set up to take these data points automatically. It could be in the future, particularly for ISO where they like to do things automatically there. Not much advantage for Nfpa. You're only taking 2 points anyway, so doing it automatically is not really advantageous. So hit the calculate. We don't have any automated calculated functions in here, so you do have to click calculate when you're going from one section to the next. So here we have a calculated hold time of 12.4 minutes. Basically, you've completed the first part of the test, which is the hold time calculation. So pretty much the same as you've done before for those people that have been testing for a number of years. Again, the only addition is taking a point at 50. What the software used to do is it would calculate the column pressure, which we can see if we expand this. We take a look at the column pressure, which is 16.35, and it would have you test at 10 or 16 points, or the column pressure, whichever is greater. In this case, 16.35 is greater, so it would have you test at 16.35. The disadvantage of that is when we change agents, we're now testing at a different pressure. Here, the advantage is that whether we're testing for an inert or a halocarbon or whatever, we do the same test and we can flip agents back and forth, and it doesn't matter. It doesn't affect the way that we do the test. So we do the test in a consistent fashion, which actually makes that in some ways a little bit easier. So here we have, we've calculated our retention time, and in the simplest case for venting, what we're going to do is we say we have no vent. When we have no vent, we're basically using the enclosure for venting, and in this case, the vent area uses 443. Now, notice there that this is the vent area used, which is calculated at 125 pascals, and that is the same leakage area that we had up here. Let's just collapse this. So this one is 257 square inches at 10 pascals, and for venting we've got 443. Let's go back to this, 257, 443. This is the value in being able to measure N, the actual slope, and find out what the true venting value will be. So exactly the same door fan test is saying, hey, at 125 pascals, which is where we measure venting, we have 443 square inches of leakage. And that's giving us two peak pressure values here. We've set the enclosure pressure limit, in this case at 500 pascals, and we pass both criteria. So super simple. Couldn't be easy, really easy for the guys in the US to do these venting calculations if they are using the enclosure leaks for venting. In this case, we've put a minimum maximum value on the humidity. Humidities in these rooms will normally run around 45–55%. So we do have to come up with a design minimum and a design maximum in order to get these values. And you'll notice, for example, if we were to change this to 10%, that I believe that value changed. Let's just change it back. Oh, there we go. 179 pascals at 30%, and we change this to 10%, and the pressure goes up to 235. So you can see it is changing with humidity. And on the positive side, if let's say we change this to 100%, we'll notice that this pressure goes up a little bit, but not enough to really worry about. So we've done one door fan test. The reason why I changed the door fan test for the hold time calculation is that we can now use the same door fan test for peak pressure evaluation, just to make your life a lot easier and enable us to have longer retention times and more venting that we would appear to have otherwise. Okay, so that takes care of that case, and I'm now going to look at a more complicated case. So I'm going to save that one, and I'm going to open this one that says vent only. So this is the same test. We're just going to collapse these down. So we're only looking at, see, we got exactly the same situation or pretty close to it. The enclosure leakage is the same as it was before. 257 square inches of leakage, and the same retention time. Might have changed some of the details. I think the concentration changed here a bit, so that's off by a small amount. Nothing to worry about. You notice that when we change this here, let's say to 7%, that changed to 12.9 minutes. So the lower concentration, being less dense, runs out more slowly, and the retention time increases ever so slightly. So more agent means it runs out faster for descending interface. Not so for continual mixing. But you can certainly experiment with the stuff just by changing them. Can't hurt anything. You always go back to where you were before. So let's collapse this down and take a look at venting. So for the ISO case, they typically design the enclosures so they say we won't use any enclosure leakage for venting. We're just going to use the vent area for venting. So what we would do in that case is we need to measure the vent area. So we'll open the vents to the degree that they would be open if they were subjected to 125 pascal pressure. We fix them in that position, and we do another door fan test. Here I got to change my signs again. We do another door fan test, pressurization and depressurization. In this case, we're on range A, so it's going to be leakier. And we're going to get 753 square inches of equivalent leakage area. And up here, we're using a gravity vent. Discharge time 10 seconds. This stuff is the same. Venting data set expresses leakage area of room and vent. So here we've got the room leakage and the vent being measured. But we're only going to be using the vent for pressure relief. Vent only. These are the different options, room and vent or vent only. So this is the typical European case. So we've gone in and have to do another door fan test because now we've got the vents cranked open, and the enclosure, which was 443 square inches at 225 pascals, is now 753 square inches. Okay. It also asks us to do the same test in the negative direction, which we've done. We just put the same values in here. Again, I'll call that a minus 10. So we've got 753 in the positive direction, 753 in the negative direction. You might say, well, gee, why wouldn't it be the same? Well, some vents will open more in one direction than the other. So our life does become a lot more complicated when we have these vents in the room and we're having to measure them, but nevertheless we've measured them. And so here we come up with 147 pascals in the positive direction, 329 pascals in the negative direction, and that's our venting analysis. But notice here the vent area used is 310 square inches. So let's go back to our PowerPoint and see what went on here. So initially we had 257 square inches at 10 pascals, which is equal to 443 square inches, 125 pascals. That was a previous example. A bit complicated, but relatively simple. In this example, the enclosure leakage is still the same. The enclosure leakage at 125 pascals is 443. That was the original, I guess, venting that was from the enclosure itself. The enclosure plus vent is 753. We subtract the two, we get 310. Come back, and that's what we've used here. 310 because we've told the software that we want pressure relief from only the vents, forgetting about enclosure leakage. So that's only allowing us to use a 310 square inches, which is the actual leakage of the vents. There's two ways to measure these vents. One way you can measure them installed in the enclosure. Another way you can actually take the vent out and stick it in a big cardboard box and measure it right then and there. And then this test here would become, the data set would be vent only. If you're confused by that, I'm not surprised, but by all means, ask us a question about your specific circumstance and we'll walk you through that. Okay, that's mostly what I wanted to cover today. Okay, I'm going to take a quick look at my slides here and see which ones. This is a dual acting vent, by the way, which will open one way and open the other way. Sometimes people use two single acting vents. Very, very important for those using ISO standard. These halocarbons usually require more vent on the negative side. I know that a lot of the calculations that you have only show positive venting. In some cases, the halocarbons require almost no positive venting at all, or venting for positive pressure, all negative. So you do need to keep that in mind. Very important point. So thank you very much for your interest, and I believe we have another one in a week. You can sign up now. We had a pretty good attendance this time around, and so the earlier you sign up, guaranteed that you can get a spot. So thank you very much for listening, and bye for now.